Our project that we chose to do this year was the paper sorter. We asked a few questions about it to some of the teachers and staff and whatnot, and some of them said that they sort their paper by hand, so we figured it might be a little bit more effective if we have a machine that does it for them. Our design statement: there is no efficient and cost-effective way to sort large quantities of paper. Like I said, here's the survey. Like I said, they stack most of their papers by hand, so we figured it'd be a lot more effective and more efficient for them to stack it with a machine such as this. In the beginning of the year, we had to make a design matrix. We kind of wanted to decide what we were going to do to make it look more clean, more efficient, any way like that. So we kind of put it right here. You can see that it says cost efficient, the efficiency to make, the capacity and height, and how easy it is to use. In the beginning, we decided that we were going to use like our smartphone to take a picture of it and sort it by that way. However, we found a little better thing that connects to the Raspberry Pi. To start the design, Boho and Bryce Beckley, they're a very good inventor, decided to make our like sides and our bottoms to make like the structure as sturdy as possible, so it doesn't obviously break down on us. This is what our initial designs look like. That is the bottom. Here are some of the sides. To continue our design, we had to add like a shelf to sort the paper into. Unfortunately, we were kind of looking at a little bit more stacks because there are 8 hours in a day for us. However, we were only able to get 4, still not that bad. That was our initial design right over there. You can see all the brackets, you can see the bottom. Another thing that you cannot see on this is that right over here, we initially designed this as like kind of like stability. We were not able to get that, but it still managed to work perfectly in our favor. Like I said before, the shelves were something we definitely needed. We wanted to find a way to make it as like effective and as easy to move around and whatnot. So Bryce had a great idea to have them fold up, so then you can kind of carry it like that with hinges attached. We bought some of the plastic and whatnot from a really sketchy place called freckleface.com, but it worked in our favor. He designed some of the sides, like right here you can kind of see, and on the project you can see he made that for stability, and so then they kind of stay together when we're folding it up.
Moving on, to be able to move our paper into the sorted positions, we are going to need 2 motors and a linear actuator. We chose a Rev Robotics Core Hex motor because of its 5-volt capacity and its ability to spin at a speed of 125 RPMs. And then we chose a linear actuator from Servo City because it's able to move up and down along this stationary rod, whereas other ones had extended out from a thing. So we wouldn't need to utilize extra space instead of just having this servo. In order for the motors to be able to turn with very little friction, we would need to use bearings on the opposite side of the motor. So we either used the Servo City bearing, as you can see right here off to the right. That one came with the mount that sat on top of one of our pieces of plastic. Whereas the other bearings, we 3D printed our own mounts for them that we designed in Inventor. These are bearings that you would see on like a skateboard. They're just everyday bearings that you can buy from a store. In the design, the motors were attached to, our first motor off to the left, as you can see here, was attached to the side of our project with a 3D printed bracket. It holds a roller with 3 also 3D printed rollers that would dispense the paper onto the second motor, which is attached to the linear actuator. This motor is different in that it moves up and down with the linear actuator so that it can dispense it to the shelves. Each roller is connected to this hex shaft that we bought from Rev Robotics that's compatible with the motor, and then it has 3D printed rollers on the hex shaft. Those are really hard to put on. We had to actually hammer those into place because therefore they wouldn't slide around. These rollers, the 3D printed material that we use isn't actually very sticky or tacky, so we ended up having to put tape around the outside of them along with rubber bands, in order best to stick to the paper and move it around. Opposite of the linear actuator, we had to purchase an X-rail slider so that the linear actuator could move the hex bars up and down in a flat fashion with very little friction. So we 3D printed a piece that would hold these bearing wheels that were at the perfect distance so that they would fit around the X-rail slider in a way that they wouldn't fall off. Before we could start building our project, we had to finish the entire design in Inventor and put it all together. So the shelves, we ended up attaching an Inventor with hinges, as you can see off on the left. And then on the right, we added the drawer, which was a separate component, into one big finished design in Inventor. To begin building, we started printing off these 3D printed brackets and the sidewalls. Everything that is this white clear plastic was the one we got off the sketchy website. And then everything else, the gray, is 3D printed filament that we got from Mr. Rader. All the hardware is also from Servo City that we bought. To assemble the first motor, we 3D printed that bracket and we attached it with the hardware. And then you can see here our rubber bands that we placed over the 3D printed rollers. This really just gets a tacky grip on the paper because the filament doesn't really stick to the paper at all. Oh, sorry. For the second motor, this one was a little bit more complicated. For this motor, we'd attach it to the linear actuator with giving it enough clearance so that it would move up and down the side without touching the wall, without touching the hardware. So for this, we had to fidget with it a little bit more to set it at the right length and to mess with the hex bars so that it's the right distance in between without messing up the bearings.
This was the drawer that goes in the front of the mechanism. Originally, it had, as you can see over here, it had springs sitting in there so that no matter what amount of papers we had inside of it, the papers would be pushed up against that tacky roller that Bryce was talking about earlier. Unfortunately, one of the design constraints we didn't think about was that this side would be constantly rubbing on the inside over there. So unfortunately, in our final product, it didn't quite work out. Something to work on the next time. Otherwise, yeah, the drawer consisted of like 3 main parts, as you can see here. Mr. Rader's 3D printer unfortunately wasn't big enough to print it all in one, so it took me another week to go back and design the joint parts right here, but it's just 3 pegs, one from this side, one from this side, and then one from the joining itself. These are the sliders that go on the bottom of the drawer. It's so that the drawer is always in the same spot, and obviously the camera can read the number on the paper from the same side every single time. It's also just for kind of a general smooth experience, because before we just had it sliding on the nuts and bolts that were kind of on the inside, so it was a little messy there. As you can see, it got scratched up a little bit. This is kind of the heart of our whole project, the Raspberry Pi and camera that me and Mr. Rader kind of jointly developed. The Raspberry Pi is basically just a very small camera, or a very small computer, and basically all we had to do was attach the camera through one of the accessible ports on it. It was pretty easy to do from there. We just had to do the wiring. So for the wiring, we needed to use one of these motor drives in order to control the motors the way that we needed to. For example, we needed some of the motors to go forward, some of them to go backwards, and the linear actuator obviously to go up and down. So as you can see on that diagram there, there's the out for 1 and 2, which is positive and negative for one of the motors, out 4 and 3, which is positive and negative for the other motor, and then the 12 volt, 5 volt, and ground on the bottom there is for the motor driver to get power itself. Yeah. And then this is the power supply that we used. We just got this from one of the old computers that were here from the school, so they actually provided it for us. It was pretty easy to wire in. We just used, I think, like this group of negative and positives right here, and then to get it working, all we had to do was wire this number 16, this PS on, into a ground just so that it would always have power going to it. These are kind of just diagrams of what we have as the camera system over here is mounted on the top, so you won't really be able to see it from just standing. And then this is how we powered the Raspberry Pi here. So this one, it's a USB Type-C. So unfortunately, we couldn't just use like a regular USB Type-C, as there aren't any USB ports that we could have used. So we had to use this sort of configuration. We just ordered it off Amazon, and it can fit a positive and negative that once again just came right from the power supply. And then over there's obviously all the wires that we had going from the motor driver to the Raspberry Pi. And then from there, it would react based off of the camera reading. This is the final product video. The numbers being read, obviously, for those who visited, it's 1 on the bottom, 2 in the middle, 3 on top. And then if it couldn't read a number, or if it's a number other than those 3, it would go to the bottom. And then right here would be what it actually ended up reading. So you'll see in the video. And then just a quick side note, I know we only have 1, 2, and 3 on there, but this is hopefully in the bigger picture, we'll be able to do any numbers, any kind of from 1 to 10, basically. So, yeah, so as you can see, it runs through the image there. Once it sees the number, it kind of crops the image, takes a photo of it, turns it black and white, and then inverses it, and then goes to where it needs to go off of there. So, unfortunately, it is a little slow, so it's like a 3-minute long video, but you get what you get. So as you can see, it's going to read a 4. So that's not 1, 2, or 3, so it's just going to end up going into the bottom drawer, as you see there. Sorry for the long video. We actually got 5 in a row here, which is why I wanted to include it, because for anyone who visited, we could only really do 1 at a time. Obviously, testing it on the same table for what was probably like 6 months, it's really easy to kind of fine tune what we needed to. When we ended up moving it from table to table, unfortunately, it wasn't as easy. If you can see down there. This one, unfortunately, did mess up. I didn't touch it, so it actually ended up fixing itself. There's just a rubber band on this side that I had to adjust to make sure nothing fell off. Yeah, so not touching anything with the paper. Still the same too, as you'll see with the computer screen in about a second or so. There's 5 for anyone counting. Now the last point I would want to make is, as you can see, after each of the papers, I kind of have to move them back with my hand. So for any further testing, we probably would have adjusted the drawers so that they were on a downward angle, so that once the papers actually go into the drawers, they kind of sink themselves down there and they'd be kind of out of the way. Because right now it would kind of stay in the way of the linear actuator. When it went up, the next paper would hit it and then it'd kind of mess everything up. So yeah, other than that, that was our paper sorter.
All right, so we have some time for questions. Anyone have any questions for this team about the design, how it works, why they made the decisions that they did, anything like that? There's got to be lots of questions. All right, I'll come around. If you have a question, you're welcome to come down to the right-hand side. Otherwise, I'll bring the mic to you. Get my exercise in.
What code are you using? What script are you kind of basing most of this off of?
I'm assuming you mean language?
Yeah.
It's a combination of C and C++.
Cool.
So the original code to kind of read the handwriting, I believe is written in C++,
Yep.
but the code after being integrated that we use just to get it from drawer to drawer is C.
Awesome. Thank you.
Okay, so I know nothing about engineering, and this is the first protocol. But what is the reason for, like, in the future when you would look forward, would you be able to adjust the speed of the sorting at some point, or why did you have to stay with the speed of the sort that you did?
Yeah, so unfortunately these are all kind of coding based questions, so they can't really answer because I did the coding. But yeah, so basically when you code something, you say on motor 1, sleep, or give it 5 seconds, then turn off motor 1. So I kind of just wanted to have as much space as possible between them to make sure nothing would mess up, or if it did, then I'd at least be able to see what went wrong and then fix it for the next run.
Other questions? I have a question for you, or at your request. Could you talk about the challenges you had feeding the paper with the rollers? 'Cause you didn't really go into that very much.
I can
It
talk about
was
this
a
one.
big challenge.
So one of the biggest challenges, other than the coding that we had, was moving one paper at a time. Paper is very, very thin, and it's very, very light. So in order to move one paper at a time without taking up a giant piece of machinery that costs way more than we can afford, he'll rewind it a little bit. We ended up having to really fidget around with the rubber bands that we were using. So if Adam wants to laser on the rubber bands here. So this was our original rubber band configuration. It was just some basic rubber bands we found in Mr. Rader's room, and it was just one line of them. We went through probably 10 different kinds, and now if you want to look at ours, we actually have a thin layer of tape on the outer ones with some thicker rubber bands, some thinner rubber bands. On the bottom, we have some thicker rubber bands lined up in a certain way so that it'll best stick up to the paper. And then even then, sometimes we would get 2 pieces of paper. So what Adam added in the code was a backwards rolling period just after we had the paper sorted. So that if there was any error, like you saw in the video with that 2, it would just roll straight back and run it through the next time.
Yeah, so you couldn't really see what he was saying. These rollers right here were actually, there was another set applied to here and here, and then when we ran the code, this one would spin the right way to feed the motors, and then there's a rubber band, like kind of around this side. It should be on your side if you want to see. It's right, it's just right here. So that kind of puts resistance on the bottom one, so that any other paper going in would kind of get caught in it and just stay there. And then, like Bryce said, if anything did get caught in it, we have it timed so it wouldn't go all the way through, so that in the backwards process, it would be rolled back to the right spot.
All right, awesome. Thanks so much, guys. You did a great job.